Hello everyone, this is Professor Roman. Welcome to the 36th video in my video lecture series, An Introduction to Discrete Mathematics. In the last video, we began our discussion of partitions of an integer. I hope we've had a chance to take a few deep breaths, so we'll continue that discussion. When we write a partition in this form, which is what we have been doing, we're describing, of course, the size of each individual part. 4, 3, 3, 2, and 1. But there's another way to define a partition, an equivalent way, by giving the number of parts of each size. And this number is called the multiplicity of the part size. And I'll denote it by this expression, MULT of S, where S is the part size. So in this partition, we could have defined it by saying the multiplicity of 1 is 1, meaning there is one term equal to 1. Multiplicity of 2 is 1, meaning there's one term or one part equal to 2. Multiplicity of 3 is 2 because there are two parts of size 3 and there is one part of size 4. It describes the same thing, but it does have some very interesting uses to look at it this way. You won't see this written out very often. Generally speaking, you will see a different notation, one of which is the use of ordered pairs. So again, let's look at this pair. This tells us that there are two parts equal to 3. So the first component is the part size, and the second component is the part's multiplicity. Perhaps an even more common notation that you will see looks like this, where the part size, the base is the part size and the exponent is the multiplicity. Okay. Kind of reminds us a little bit of exponentiation. For example, 3 to the superscript 2 says there are two terms of size 3. 3 squared means two factors of times equal to 3. So there's kind of a resemblance there. It might help you remember the superscript is the multiplicity. Okay. So when describing an arbitrary partition P of an integer k, one thing we know, of course, is there can't be a part of size bigger than k. So the part sizes will range from 1 up to k. And some of those sizes will not be present in the partition. But in any case, we can list the multiplicities of the potential parts 1 through k. So some of these values might be 0. This is the exponential notation. I'm sorry, this is the order pair notation. This is the exponential notation. So for a specific partition, we would generally leave out the parts that have multiplicity 0. There's no point in writing them. So a partition like this would be written with 3 ordered pairs because the part sizes that appear here are 1, 3, and 6. There are 2 1s, 2 3s, and 1 6. And in the exponential notation, it would look like this. In any case, a partition of the integer k is uniquely determined by this equation involving the multiplicities of each part. And I'm going to call this the multiplicity equation for k, for this partition of k, although I don't think that's a standard term, so you might not hear it anywhere else. But it seems reasonable. So the number of partitions of K is the number of solutions to this equation, which gives us the multiplicities for that particular partition. If we also want to specify that the partition should have exactly n parts, then that's described in terms of multiplicities by this equation. The sum of the multiplicities would then be equal to the number of parts, which is n. Well, I've already mentioned that there is no formula for the number of partitions of a certain integer, a general formula. But the question remains, how many solutions are there to an equation like this? Well, we can get a partial hold on this by making a rather clever observation. This equation kind of reminds me of something, and I can't quite sort it out. But if I put this expression in as an exponent of a variable x, and I break it up like this, it's beginning to become even more suggestive. This now is a polynomial of degree k. In fact, this expression appears as one of the terms of degree k in the expansion of this product of formal power series. To get this expression, what do? Well, we take the x to the m1 term from these formal power series. We take the x to the m1 term from here. We take the x squared to the m2 power from here, and so on. And when we take those terms, we multiply them, and we'll get this. So this is some progress. We're beginning to recognize this expression and where it comes from. We can clean this up a bit because this formal power series, of course, the powers of x, is a 1 over 1 minus x. And this one here, for example, is 1 over 1 minus x squared. We just put x squared, replace x by x squared. In the first factor, we'll get this one. By the way, something else that's going to come up, and I'll say it now. If we're looking for a term of degree k in this product, we don't need the infinite formal sums here, formal power series. We can truncate these at degree k because higher order terms will not enter into the coefficient of the any degree k term. Okay, so we're not really faced with multiplying infinite these formal power series together. We're faced for any particular k in a product of polynomials. Okay. And I'll return to that theme a bit later. Okay, so this isn't quite as bad as it might look. Okay. But in any case, this can also be written like this. Okay. Now, it's important to understand what's going on here because, as I've said several times before, this gets confusing. This is not easy stuff. Okay. By picking a term from each of these factors and multiplying them together, to get a term in the expansion of degree k, what we are doing from each of these factors is picking a multiplicity. We're picking one of the m's. So I might want to refer to this expression, this is an arbitrary one of these factors, as a multiplicity selector for that particular part size. So to put it bluntly, if we choose this term from this expansion, so x to the s to the power m, what we are doing is specifying that the part size s has multiplicity m. In other words, there are m copies of s in our partition of the integer k. And, of course, these multiplicity choices have to satisfy this equation, the multiplicity equation. In any case, now we can say that there's a bijection between the terms of degree k in the expansion of this thing, or written this way, of the expansion of this, there's a bijection between these terms in either of these expansions and the partitions of k. And the description is that we are choosing the part multiplicities. So once these part multiplicities have been chosen, this is the actual partition. There are mk copies of part size k. In other words, there are mk terms equal to k, mk minus 1 terms or parts equal to k minus 1, all the way down to n1 terms or n1 parts, m1 parts of size 1. Let's take a look at an example that might help clarify what's going on, hopefully. Number of partitions of 5 is the coefficient of x to the 5th in this product. So this is the same as, where are we here? Yes, same as this, but for k equals 5. So we have 5 factors. This is f of x, this is f of x squared, f of x cubed, f of x to the 4th, f of x to the 5th. That's also right here. Now, the first thing we can do is immediately simplify by removing terms of degree greater than 5, because a term in any of these formal power series of degree 6 or greater is never going to contribute to a final term of degree 5. So we can shorten this first one to 1 plus x all the way up to x to the 5th. This one we can terminate at x squared squared, because x squared cubed is x to the 6th. And the next term here is also x to the 6th, then x to the 8th. So we don't need any more terms. This is all we need in order to extract the terms of degree 5. Now I'm going to write this one time only, because it was a pain in the neck, a little bit differently to expose exactly what we are doing. So this first one, for example, I have replaced 1 by x to the 1 times 0, because if we pick this term from this multiplicity selector for part size 1, we are saying there are no 1s. there are 0 copies of 1. X means 1 copy of 1. X squared means 2 copies of 1, and so on. X to the 5th means 5 copies of 1. This is the multiplicity selector for part size 2, 0 2s, 1 2, 2 2s. For part size 3, we either have 0 3s or 1 3. We can't have 2 3s. That's already degree 6, and so on. So this makes it pretty clear how the multiplicity selector works. The selection of x to the sm from f of x to the s power shows that what we are doing is selecting m copies of part size s. So in the partition there'll be m terms equal to s. So now we'll collect the terms of degree 5, and it's easier to do that from this expression here. I can take x to the 5th, then I have to take all 1s, so that's this one. I can't take x to the 4th because there are no x terms equal to x in any of the other factors. I can take x cubed times x squared, and then I have 3 1s that I have to choose, and so on. I'll let you go through the rest of this. Okay, this is just little algebra. So I've got the terms that of degree 5 that come from this. Okay. Oh, let's see. I had to fix that one. That's x to the 5th here. Okay. Now, what I'm going to do is go back to this other notation that helps expose what's going on. This x to the 5th came from the part size 1, so it's 5 copies of 1. This is 3 copies of 1 and 1 copy of 2. Be careful here. This x squared is this x squared, and it's this x squared. It's 1 copy of part size 2. And then no other part sizes. That's x to the 5th. Okay, this one, x squared, comes from the first one. It is 2 copies of 1. So where is that? Let's see which one. Oh, I'm sorry. I skipped something here. Oh, it should be up here. Yeah, 2 copies of 1. And that's right here. And then 1 copy of 3. So that's right here. And I'll let you go through the rest of these because this is testy. I mean, you have to really concentrate on what's going on, which is why I wrote this out. Okay. It might have even be clearer, rather than writing this, to have actually written out, instead of x to the 5th here, to have actually written out x to the 1 times 5. Okay. But you got to get used to doing this, and it's tedious, and it's easy to make a mistake. But this is what I got, and there are 1, 2, 3, 4, 5, 6, 7 terms of degree 5, so 7 x to the 5th. That's the term of degree 5 in this product when you write it all out. Okay, and these are the individual parts that make up that term. Okay. So how many partitions are there of 5? There are 7 of them, and they are described right here in terms of multiplicities of part sizes. So this first one is 5 copies of 1. The second one here Oops, if I can do that. Okay. This is 3 copies of 1 and 1 copy of 2. One more. This one is 2 copies of 1, 1 copy of 3. So we get the actual partitions. And we know there are 7 of them. This is the same list that I gave you in the previous video. And this is where I got it from. Okay. Because I knew I wouldn't miss anything. For small integers, you can reason it out just by, I think I had the list in the reverse order, or in a different order anyway. These are not, I didn't write these in decreasing order of part size, because as we know, that's not required, it's just a custom. But to match the exponents here better, I left it this way. Well, there's one more thing to note, and that is if instead of taking the product here, f of x through f of x to the k, and expanding it, I'm still looking for the terms of degree k, because I'm partitioning k. If I include the next factor, which is this one, does it make any difference? No, because including this factor, which is the powers of x to the k plus 1, only the 0th power will be involved in the extraction of the terms of degree k. Only the constant term. So it changes none of the computations that we just did. Which means I may as well include all of them. Okay. And so, in other words, this becomes an infinite product. Okay. That way I can find the terms of degree k for any k. Okay. In other words, I can find the size of the number of partitions of k for any k. It's the coefficient of x to the k. That's the generating function. Capital P of x is the sum of P of k x to the k, the generating function for these, for these numbers, and it's this infinite product. Well, this isn't the most pleasant of generating functions. It's an infinite product of infinite series, but it's something. It's probably an indication that these numbers, P of k, are not so easy to find. And that's why nobody's found a formula. While this generating function may not be very useful in actually computing P of k, the technique that we use to obtain the generating function can give us some very interesting results, and we'll look at that next. For example, suppose we want the generating function for the numbers, which I'll call Q of k, of partitions of k into distinct parts. That means the multiplicities are either 0 or 1. And so a partition of this type is going to have this form where the deltas, delta sub I, is either 0 or 1, the multiplicities. And that gets identified just as it did before. This is the setting this equal to k is the multiplicity equation. I've just changed the m's to deltas because I want to make it crystal clear the multiplicities are either 0 or 1. So what is the this term in this product, which again is this product of infinite series? We can truncate again, but now we're talking about degree at most 1. So all we need to do is keep this much. Sorry, I didn't say that right. All we're talking about now is multiplicities of size 1. So in our multiplicity selector, see, this would be 2 copies of 1. Little typo there. This would be 2 copies of 2. We can't have multiple copies, so it reduces to just this. So a partition of k into distinct parts corresponds to a term of degree k in the expansion of this polynomial. And so the generating function is this product. I'll come back to this in a minute. We have more to say here about this. Another example. Suppose we want the generating function for the numbers s of k of partitions of k into odd parts, 1, 3, 5, 7, and so on. So a partition of that type is going to look like this. The only part sizes we represent are k, and to make it simpler so I don't have to have 2 different versions depending on whether k is even or odd, I can just say mk is 0 if k is even. Okay. And that gets identified with this polynomial. And so we need to extract a term of degree, or all the terms of degree k, from this product. This is f of x, this is f of x cubed, this is f of x to the 5th, and so on. So it looks like this product. So this is the generating function for the s of k's. So we have this generating function for partitions into distinct parts, and we have this generating function for partitions into odd parts. And here they are again. Well, what's not apparent, but we're going to discuss now, is that these are the same generating function. They look totally different, but they're not. Okay, well, the first thing to notice is that both series have constant term 1. It's pretty clear from this one, and I'll let you ponder this one. We want to examine the coefficients of x to the k in both products to show they're the same. We could do this directly using these infinite products, and in fact that's the way I wrote this initially, but I became concerned that that would require some justification, manipulating these infinite products in the way we do, and I didn't want to have to get into that because it takes us too far afield. So we're going to do what we did in the examples and cut down these infinite products. Okay. So we're looking for the coefficient of x to the k in both of these products. The coefficient of x to the k in this product is the same as the coefficient of x to the k in this product, because the next factor and subsequent factors you would have to you'd have to take the term equal to 1, the constant term. Otherwise, the degree will be greater than k. And same thing works here. And it's a little, all you have to do is write this out as an infinite series, and you'll see that you're going to have to grab the constant term in order to get terms of degree k. In fact, some of these are even going to be too big. We don't need them, but to cut back down here to even fewer factors would mean taking cases and stuff. And I want these two to be the same number of factors, even if some of these are unnecessary. So now we do some algebra on this guy. Okay, so that's right, whoops, that's right here. First, I'm taking out the m equals 0 factor. So now the sum goes from 1 to k. And for each of these, I'm multiplying and dividing by the same quantity. We're dealing with polynomials now. So when m is 0, you see, this would be, the numerator and denominator would be 0. So I can't have that. So that's why I pulled this one out. Okay. Now I'm going to break this up a little bit. These factors are right here, the product, and I split this one into two products. Okay. No question that this is legal because we're dealing with polynomials. We know we can add, subtract, multiply, and divide. Okay. Now I've simplified it to this. Okay, so we have to take a close look here and see what's going on. This starts at m equals 1. And so this is going to be 1 over 1 minus x cubed. And this is going to jump up with each factor by 2. So this will be x to the 5th, x to the 7th, and so on, starting at x cubed. And so these exponents are odd. These exponents are even starting at 2. So if we just look at denominators and we collect all this together, we're going to have 1 over 1 minus x squared, then x cubed, all the way up to x to the k. This is 1 over 1 minus x to the 1. So all of this, and where does it stop? It stops when m equals k here, and I get 2k plus 1. This only reaches 2k. So from 1 to 2k plus 1, I have all these factors. When m is 1, I get this factor. When m is 2, I'm going to get this factor for m equals 1. And so on. You may need to think on that. I had to myself. And then I just reproduce this one. What next? Well, I split this product. Here is m goes from 1 to k of these same factors. And here picks up at k plus 1 and goes to 2k plus 1. And the reason I did that is for the next line. And the reason I put this upper half of the product, or upper part of the product here in front, so I just duplicated it here. But look at this other part. Okay. M goes from 1 to k in both cases, but I have 1 minus x to the 2m divided by 1 minus x to the m. Okay. This I have reproduced as the second factor. What about this? Well, 1 minus x to the 2m is 1 minus x to the m times 1 plus x to the m. This is the essence of this whole computation. So there's a cancellation, and I have this sum. That is this, which is a piece of, which one? Of Q. This is a piece of S, the product up to K. It's what they call a partial product, just like a partial sum of an infinite series. This is the kth partial product for which one for S. This is the kth partial product for Q. We still have this factor. But remember why we're doing this. We're trying to examine the coefficients of x to the k on both sides. This does not, this does not contribute to that coefficient. So the coefficient of x to the k in this is the same, it's right here, as it is in just this part. Now that holds for all k, arbitrary k. We didn't specify k has to be restricted in any way. So I can replace this k by an infinite sign. And we have the infinite products. Their coefficients match. So the series are the same. The generating functions are the same. Okay. Take another deep breath. This proves a result that was first proved by Leonhard Euler in 1748. That's the year after I was born. The number of partitions of an integer k into odd parts is equal to the number of partitions of k into distinct parts. That's pretty amazing. I mean, the result seems, a little strange, but it's true. What's amazing is that we were able to prove that, even though we don't have formulas for the number of partitions of an integer. The generating functions got this for us. Well, in conclusion, the theory of partitions of an integer is a very important area of current research in mathematics, obviously, because there's so much we don't know. Entire books have been written on this question. And again, no one has found a formula for P of k, the number of partitions of an integer k. We have some small values here. Remember, P of 5 equals 7. We found that ourselves. Values of P of k for large k have been computed using computers. For example, it's quite obvious that P of 1000 is this number here. Okay, there'll be no debate on that. Various facts are known about these numbers. Euler also showed that P of k is equal to this nasty looking sum involving P of other values. Okay, I don't even want to think about this, but it's the kind of it's an example of the kind of stuff we do know. But the sum is taken over all the non-zero integers I, with the assumption that P of I is 0 if I is less than 0. As I say, I don't even want to think about this. I just wanted you to see it. A fair amount is known about divisibility, stuff like P of 5k plus 4 is divisible by 5 and things like that. I don't know where these came from. There's an approximation formula, and it's fairly good. So P of K is approximately equal to this mess here. I think all this shows that we have a long way to go in understanding partitions of an integer. So it's a bit curious that we can decompose sets into blocks and partitions of sets and permutations into cycles. But when it comes to decomposing an integer, a positive integer, we got a lot more to do. Okay. All right, so that takes care of partitions of an integer, and we will move on to the last section in our advanced combinatorics material, counting almost everything else, Catalan numbers. So thank you for watching, and I hope to see you in the next video.